Okay. Okay. Let's quickly review what we have learned about transmission line. Uh, first, we study if the transmission line is I use a thick wire. If transmission line is long enough, okay, it's infinitely long, okay, then we discuss the electric property of a transmission line can be described by a circuit model, okay, by a circuit model. This is say if we are talking about very short transmission line, right? Okay, that can be described by this circuit model. This circuit model, we have series inductance, so that all per unit length, okay? Okay, inductance, we have a capacitance, okay, between two conductors. We have inductance on one conductor, right? So we have a loss, okay, we have a loss, R, L, C. Then we also have conductance, okay? Okay, with this full circuit model per unit length, then we can determine two very important parameters. That is the only electrical parameter that describe transmission. One is propagation constant. Okay, gamma. Okay, one is the gamma. One is characteristic. Impedance. Okay, so these two can be the only two parameters that describe transmission line. Okay, so with this circuit model, we justify the voltage and the current satisfy the wave equation. Then we can set up a differential equation. We can find its solution, voltage and current. Then we can justify the propagation constant equal to this. Okay, and also that expressed in terms of the RL CG, right? And also the characteristic impedance is described by this, right? So in lossless case, okay, the lossless case, so you only need to remember lossless case, okay? So that is L over C. Okay, then the gamma become G beta. Okay, so that is sorry. Okay, is that easy to remember? Okay, so no. Beta is G beta. Beta is G omega divided by phase velocity. Okay, so phase velocity is 1 over L/mc. Okay, so therefore we get everything we need, right? So this is for infinitely long transmission line. And later on, we studied, okay, for finite length of transmission line, we load with arbitrary loading. Okay, this is arbitrary loading is a complex. Okay, which is complex. We have a real part and imaginary part. Okay, then we can derive at any point, okay, if this distance is L measured from load, okay, we can find there is impedance looking into the load. This impedance can be very well described, okay? by beta. We already know what the beta is. Okay, then we also know the distance to the load. Then we can know the impedance. So this impedance, this is the total voltage divided by total current. Okay, so if we are talking about this, we call reference plan, right? For given reference plan, we can find what is impedance, and also we can find what is the reflection coefficient. Okay, so this impedance is defined by the total voltage and the total current. So this definition is the same as our circuit theory. Okay, same as our circuit theory. So voltage divided by current is impedance. However, for transmission line, impedance at different location is different. This is very important. Okay, this is very important. So this formula we must remember. If you couldn't remember it, learn how to derive it. Okay, that takes 2 minutes. Okay, that takes 2 minutes. We can derive it, right? Okay, we derive it. This is so far what we had. Okay, and also we said if you know the impedance, this is basically impedance at the location L. Okay, if you know the impedance, if you know the characteristic impedance, okay, then you can find the reflection coefficient at any place. Okay, down the transmission line at any reference point, right? So this general formula we explain, there is a very clear picture is gamma 0 is a reflection coefficient looking at the load. Okay, looking at the load. Then the gamma equal to gamma 0, then we have 2 times. Why is 2 times? Because the wrong ticket, right? The signal go from here to here, then has a reflection. So the wave travel 2L distance. Okay, so that creates a phase difference. Then the wave from here hit on the load, and then the reflected wave multiplied by its reflection coefficient and then come back. So, okay, so we can use this property. We can use this property to describe a general expression for reflection coefficient at any location. At any location. Okay, this is so far the most important 2 conclusion. Okay, one is impedance, total impedance. One is a reflection coefficient at any given reference plan. Once we understand this, we can use these 2 parameters to describe voltage and the current down the transmission line. Okay, so one of the basic properties, say, let's look at the voltage. Let's look at the voltage. You see, because if voltage is known, current is known, right? Because the voltage is composed, total voltage. The total voltage is composed by 2 parts. Any total current, total voltage, composed by 2 parts, composed by 2 traveling waves. One propagating in z direction, one propagating in minus z direction. Okay, so if you look at this wave, okay, this is measured in terms of z prime. Z prime is measured z prime is measured from load. Okay, is measured from load. Okay, so therefore we have 2 waves. In this case, this wave is propagating toward. Okay, now is we don't use positive z or negative z anymore. We call this is toward low. Okay, so this wave is toward south, right? But no matter what we call, this is traveling wave because this is proportional to an exponential function. Okay, once we correspond to proportional to exponential function in terms of phase, that is traveling wave, right? So because this is traveling wave, okay, this is traveling wave, this is traveling wave. So therefore, for current, both separately, this term and this term, we can divide by characteristic impedance. Okay, don't forget for travel to the south, this is a travel to the south. Right? So to the south, that is the negative z direction. We have a minus sign. Okay, we have minus sign. So we have repeat many times. So let's look at the voltage. Let's look at the voltage. Okay, so the voltage expression in terms of what is this? This is a reflection coefficient at z prime. Okay, so therefore we can say the voltage magnitude has a maximum, has a minimum, right? So if 1 plus gamma is a complex number, we justify, right? So we justify if this is 1, if this is a gamma, if this is 1, so this is 1 plus gamma. Okay, this is 1 gamma. So only 1 gamma is a real number. Only 1 gamma is a real number. So the voltage, okay, the proportional to this, right? So voltage is proportional to this. So the normalized voltage, you can say the voltage divided by IL ZL plus Z0. Okay, so the voltage reached to maximum or minimum 1 gamma is real. Okay, voltage maximum or voltage minimum 1 gamma is real. At what time gamma is real? Gamma is load, right? If this is a lossless transmission line, I use ZL. Okay, the characteristic impedance. So 1 gamma is a real number. Gamma is a real number only when the load is real, right? Only when the load is real. So this is very important. When load is real, okay, the voltage either you reach to maximum or reach to minimum, right? So the minimum proportional to 1 minus gamma absolute value, okay, or plus gamma maximum value. This is for both maximum and the minimum, okay. And we define very important parameter we call standing wave ratio, okay, or we call SWR, okay, or S. This is how that is defined. Okay, I can tell you we have a question about this in final exam, okay? So if you ignore, okay? Then we use voltage maximum, voltage minimum to define standing wave ratio. Because what, from standing wave ratio, okay, we can, you see, because look at the definition of standing wave ratio. That is always larger than 1, right? Larger or equal to 1. That can be infinitely large if gamma absolute value approach to 1, right? But however, the reflection coefficient magnitude always less or equals than 1, right? Okay, this because this is a reflection coefficient, you cannot magnify the magnitude. Okay, right? In this case, by this definition, we have, because this is always larger than 1, right? So we can say we have 2 scenarios if the load is resistive or real. Okay, one is defined by this is RL divided by Z0. If RL larger than R0, okay, Z0 equal to R0 for lossless. Okay, this is this case, or less than R0. Okay, so therefore, depending on you're looking at voltage maximum or voltage minimum, because we can measure standing wave ratio, then we know the resistive load value is that reference point. This is why this is a standing wave ratio is important. Okay. For example, you say, for example, I joke here is if you, oh, by the way, voltage and current is just opposite. Okay. Once the voltage reach to maximum, current reach to minimum. Okay. The reason is clear. You see, because the voltage here is maximum, but current here is minus. Voltage here is plus. Right. Okay. I'm sure you can figure it out. Then let's say if this is a voltage, because you have a reflection, so you have a maximum, you have a minimum. Okay, so this is a V maximum, right? This is a V minimum. So if your observation point is here, maximum, okay, then you see load is real, and also load is real. And how to find the load? The load is real, but I know load divided by characteristic impedance is standing wave ratio. So therefore, load value is, if this is given, this is measurable. Okay, this is given. Can you find this? Of course you can, right? Of course you can. So that is why standing wave, and when you design the antenna or when you purchase the antenna, okay, the basic specification that tells you, okay, in your working frequency band, what is the standing wave ratio? Okay, this, if you don't know this, if so, even you don't know how to buy an antenna, okay, or buy any other RF component, it will tell you, okay, what the standing wave ratio is. What does that mean? Is standing wave ratio. If we know standing wave ratio, we know reflection coefficient, magnitude. Okay. And also standing wave ratio magnitude is constant. You see why it's constant? Look at this definition. Okay. So if I take a magnitude of this, so that means I take a magnitude of this, right? So this magnitude equal to this magnitude, right? Okay. Then if you look at this magnitude, what does it mean? Okay. That means your load, right? This is load minus characteristic impedance, load plus characteristic impedance. Okay. The complex number, this is independent to the location. Okay. Of course, you have a magnitude and phase, but this magnitude is independent to the location. Now let's look at the very common problem. These two slides, if you can understand well, okay, if you understand well, you should get at least 20% of mark. Now, okay, now let's see. Assume this part, I don't know, okay? I don't know this part. So what I know is I have a load, which the load, I don't know what the value is, okay? But what I know is, okay, what is known? Okay, what is known is standing wave ratio. Okay, characteristic impedance. Okay, characteristic impedance for this transmission line is known, so this is very common. Okay, this is very common. Okay, I know these two things, but what need to know? What I need to know is load. Okay, so this is a question, how we do it. Okay, how we do it? Okay, first to find this, we need to find. Then we need to find what is a wavelength. What is wavelength? Okay, then if we can find, okay, find the wavelength, that means I also know the location. The location of V minimum and the V maximum. Locations, okay? I can find locations. So I find this is minimum. This is also minimum. Okay, so between them, this is what? This is a half wavelength, right? This is half wavelength. So therefore, from here, I know what is a wavelength. Okay, what is wavelength? All right, now we also know, okay, we also know one more thing is I know the location from my reference plan. You see, because I know the local location, right? So I know this is a D, okay? I call D minimum. Why I call D minimum is I know from my reference plan, this is important. This is my reference plan because I need to find the load. It is a reference plan, okay? It's a reference plan. So I know this distance. That's all the things I know. I know S, I know characteristic impedance, I know location of this, I know this. Because all this can be measured. All this can be measured. Now, okay. Now, what my idea is, okay, let's take this cover out. Okay. What is my idea is, if, okay, because I know at this point, what is impedance, okay? Because this is voltage minimum. I said, if you know the voltage minimum, then you'll know standing wave ratio, you'll know characteristic impedance, you'll know the load, right? So I know the load at this point. Do you agree? Yes. Okay, of course you know this, because impedance repeat every half wavelength, because this is also voltage minimum. It's same value, okay? So if you extend this, of course, you know this point, okay? You know infinite number of points, but those points are not interest me, not interest me. But I like to know this point. If I can find the ZL at this point, because this point is equal to this point, do you agree? Of course you know, right? Equal to this point. If this point is equal to this point, right, then I can find, you see, because this distance is known, this distance is a half wavelength. Do I know this distance? I call Lm. Of course you know, right? So if you know this value, you know this distance, can you find this Z? This is my load. This is my load. So that, of course, you know. You see, because go back to say the important formula I ask you to remember is this, right? I ask you to remember. So in this case, this L is minimum, right? So this is become the impedance right? This is impedance at the voltage minimum. Okay, this is Z0, right? This is characteristic impedance, Z0. This is a Z0. Beta, okay? So the beta, remember this is, that can save your life. Okay, beta is 2 pi divided by wavelength. You know wavelength, do you know pi? Of course you know pi, right? So what you don't know? What you don't know? In order to find, this is my load. This is my load impedance. This is the whole idea, okay? We can measure the characteristic of the load impedance by extend the voltage pattern artificially, okay? Imaginary pattern, okay? Toward the load or outside of the load, okay? Because this pattern will continue if the load is invisible, okay? So this standing wave ratio doesn't move. For giving load, it doesn't move. So this standing wave, this voltage standing wave can be measured. So next example, I'll show you the device that can measure this. Okay, using this way, we can find impedance. Now you also understand why it is important we look at a different scenario to use the standing wave ratio. Okay, to use standing wave ratio. So if you couldn't remember which is which, okay, easy, right? Standing wave ratio either or, okay, you only have two options, okay, depend on how to ensure standing wave ratio. Oh, standing wave ratio is always a real number, okay? Standing wave ratio is always larger or equal than 1. All right, okay, so in this case, larger than equal to 1, of course, the load is large, right? Okay, so this case, if load is large, okay, if load is large, then when load is larger than characteristic impedance, okay, we are having voltage maximum. Okay, we are having voltage maximum. Okay, if the load is smaller than characteristic impedance, then we reach the voltage minimum. Okay, so that's why you see it depends on you like to use this or you like to use those information. Okay, in this example, we use this information. Okay, voltage minimum information. In this case, the load is always less than characteristic impedance. Right? Okay. Now let's look at one particular example. Okay. Say this is a device. We measure standing wave ratio and also we measure the location of voltage minimum. Okay. So because this is a waveguide, so we are going to discuss tomorrow how to describe a waveguide using EM theory. Okay, so this is rectangular waveguide. So if you cut a very thin slot along the central line, okay, then you don't disturb the field. Okay, you don't disturb the field. So that means we can measure, then we can put a probe. Okay, we move the probe back and forth. Okay. This is voltage probe. We move. Okay, back and forth. We move the back and forth to measure voltage minimum. So basically, voltage maximum, because we measure this curve. We measure this curve. Okay, we measure this curve. This is a device. When I was a graduate student in 1982 to measure antenna. Okay, so but nobody uses it right now. But we still have one in our lab. If anyone you're interested, you can contact me. So then we have a diode here. Okay, we have a diode. So to convert field into a voltage, then we can measure this voltage. How? Okay, now let's see what our problem is. So we measure the voltage. Okay, we can measure the standing wave ratio is 1.5. This is one question. One no, right? We also know, you see, first of all, we short circuit. Okay, I short circuit. That means the voltage equal to 0 at this point. I short circuit. Okay, the voltage equal to 0. First of all, I short circuit. Then I can measure. Of course, this is the one location is my reference plane. At this location, the short circuit. Okay, short circuit. Then, because when you short circuit, of course, the voltage is minimum. Voltage equal to 0, right? Voltage minimum. This is also voltage minimum. This is also voltage minimum. At 0.2, 2.2, 4.2. So that means the half wavelength is what? Is 2 centimeters, right? The difference is 2 centimeters. Okay, now we know the wavelength. Now we know the wavelength. We also know the location of our reference plane, right? Okay. Now I put a load. I put the antenna at this location. Now I connect antenna, let's say a home antenna. Okay, this is a waveguide. This is like a home. Okay, so this is a like antenna. Okay, so we have a radiation. Now we need to measure this antenna impedance. How we measure impedance? Okay, I replace a short circuit by the antenna on the test. This is antenna under test. Okay. Now I found, okay, the minimum location changed. Minimum location become 0.72. Of course, this must also, because wavelength doesn't change. So that repeat every 2 centimeters, right? Every 2 centimeters. So let's find the load impedance. Let's find load impedance. So in this case, what we like to find? We like to find the extension of this, right? So we like to find what is this, okay? Then what is this? So what is this is, if this, the impedance at this point should repeat every half wavelength. So, right? So every half wavelength. So you can either we extend this point to here, right? Or to here. This is one way, right? Or we can find, you know, because we know this location, right? Because we know this location. So this distance, if you can find this Lm, you win, right? Because we already said, if you find Lm, you go back to use this. This is Lm, right? The whole thing is to find Lm. So can you find Lm? Can you find Lm? You know this absolute location. Say if this is there, I also tell you this is a 0.72, right? 0.72. Then from this, if this is 0.72, if this is 0.72, and then 0.72 plus Lm should be equal to half wavelength, right? Okay. Then you find Lm. We have a different way. Okay. You can have different way to calculate this. Right now, what I tell you is the most, I think, is the easiest way to understand. Okay. So once you find this Lm, okay. Once you find this Lm, then we can find if this is Lm, then we also know the standing wave ratio. We also know, so you don't need to use this formula. Okay. Don't look at this. Don't look at it. Look at the simplest way, the easiest way. Okay. The way that you use this formula, okay, to get your answer. Okay. So what formula is? The characteristic impedance equal to, okay, equal to ZL okay. So that is it. So you only need to remember one formula. Okay. I don't like to get you confused. I don't like to get you confused by other explanation. Just using this. Okay, just using this. And this, how this is obtained? You find voltage solution, you find the current solution, you find the voltage solution, you find the current solution. Take a ratio. You can find this. Okay? You can find this. So everything I talk about, you say, using the unified equation, right? And then as simple as just press one button. You know why I first use Apple phone? I found, you say, if you try to do anything, if that only need to press one button, it never asks you to press two buttons. So that is a very innovative philosophy, right? And then the people like to use it. Okay, so and this formula is too cumbersome. Okay, don't look at this. Don't look at this. All right. Okay. So that is the way we can find ILM. Okay, we can find ILM. Okay, so we can stop here. This formula very important. We need to remember. And if I still have few minutes, and then let's make a summary, right? And we also very easy to remember the reflection coefficient at the load right, is the load minus characteristic impedance, load plus characteristic impedance. But however, the load, so-called load, you can define the impedance at any location as a load. Okay? You can define, let's look at the general diagram. Let's look at this. You can see this is my load. Okay? Sure, this is a physical load or load on the test is fine. Okay? Then if you have a new reference plan, you can find impedance. This also can be a load. But load looking toward the load side, okay? Toward the load side. This is also load, okay? Then you can find a reflection coefficient. This is a load, ZL. You can find the reflection coefficient. I use 0 to indicate the very original reflection coefficient. But however, this reflection coefficient is just a function of location. That's it, right? And then this two has a simple relation. I said it's a two-way ticket. Two-way ticket. Okay. So the two means round way, right? And every time we use minus J beta L of beta Z means the wave travel toward the Z direction and then has gone that distance, right? Right, that distance. So when we look at this, we know, oh, this is a traveling wave. the Kelvin wave. Okay. So that's all we need to remember about transmission line. Okay. Oh, sure. Standing wave ratio. Okay. We just have 1, 2. Okay. And the standing wave ratio, or sometimes called S. Okay. That is the voltage proportional to voltage maximum and the voltage minimum. Okay. Voltage minimum. All right. So the standing wave ratio S is related to their load, real part. Okay. Real part of the load compared to characteristic impedance if larger than this, right? Or this, reverse it, flip it. Okay, if you flip it. All right, so the impedance repeat every half wavelength. And then also quarter wavelength is very important, right? So the quarter wavelength, oh, sorry, I still have another material to discuss. We don't have time. Okay, so the impedance for every quarter wavelength is reversed, right? It's flipped. Okay, inductance become capacitance, capacitance become inductance. Okay, tomorrow we talk about impedance matching. Okay, we talk about impedance matching. Also very important, that takes another 20-25 points in final exam. All right. Okay, let's stop here today.